Okay, so our last lecture then, as I said, is going to be on elastic wave propagation. And you will see that it's not too difficult. It comes naturally out of the equations of linear elasticity that we have already used and already developed. So that's going to be one of the main assumptions here, and if we have time, we'll talk a little bit about how to relax that assumption later on. And we're going to make this discussion then mostly in the assuming that we have a linear elastic solid. First, we're going to talk about the quasi-static equations, and then we talk about the dynamic equations. So by now I hope that you remember and you know how to write these equations. What are the three equations that we need for any continuum mechanics problem? Equilibrium, kinematic, and what else? And the constitutive equations, right? Equilibrium equations is the divergence of the stress tensor plus the body forces that we said that was equal to 0 to be in equilibrium, right? And this is why this is called quasi-static. Basically, we're telling that those are 0, but if you wanted to express that in physical terms and not that much in mathematical terms, you will say that the inertial forces are much smaller than the stresses or elastic forces and also the body forces. So basically that's what we're saying. And then this one, kinematic, we compute strains and it's no pointing here. The gradient of the displacement field plus, what am I doing here? This 1/2 plus the gradient of the displacement field transverse. This is our kinematic equation. And last, here is where linear elasticity comes. Stress tensor is equal to stiffness tensor times strain tensor. So the next step that we did after putting all these equations together is to combine them into a single differential equation. Do you guys remember what was the name of that? That goes into what is called the Navier's equation, and that is equal to this equation I'm writing right now. We derive this one step by step, and we show that how this equality holds depending only on displacements. That is equal to 0. Well, in that equation we use what are called the Lamé parameters. That made the derivation a little bit easier. We're going to come back now and use other parameters that are going to make the derivation of the wave equations also easier. And this first Lamé parameter, lambda, we can express it in terms of the constraint modulus and the shear modulus. And the second Lamé parameter, we already know that that's equal to the shear modulus, right? And that's something that we already know, okay? Nothing new so far. Well, let's go now to the dynamic equations. In the dynamic equations, we are also going to solve the same equations that we solved before. But what do you think is going to show up now in the equilibrium equation? It's going to show up time and inertia, right? So we're going to have our body forces, but now this one is not going to be equal to 0 anymore. And now the inertial term, before I write the inertial term, stress, remember, it's a concept that is linked to area, so it's force per area. And inertia is, we know that it's mass times acceleration, right? But we cannot write mass here. We need to write this in terms of volume. Mass per unit of volume is density. So density goes here, and here we have the second derivative of displacement vector 2 times in time. But remember that this density, if we had an element, let's say this is 1, 2, and 3, and I have an elemental cube. If this one has mass m divided dx1, dx2, dx3, that is what's going to give me mass density. It's mass per unit of volume. And when we also work with these equations, now we're going to tell that this one, in order to make it easier again, that one is equal to 0, or that the body forces are much smaller than the elastic forces and the inertial forces. The kinematic equations, do you think that those are going to change? No, those are the same, okay? So I'm not going to write them. And consider the equations, we're using the same theory again. So those are going to be the same too. So let's try to write now the Navier's equation in terms of the dynamic equilibrium equation. So if remember that in order to get here, what we had to do was to put the strains, to put this stress in there, and since now we have this equation in there, we had strains. In order to replace that into strains, we need to put displacements in there, but everything we have to do is just to add this term. And I'm going to add this term, and I'm going to use constraint modulus and shear modulus now. So what is lambda plus g in terms of constraint modulus and shear modulus? M minus g, right? And this part of the equation is going to be the same. So now I have the here divergence of displacement plus g Laplacian of displacement, and now it's not equal to 0 anymore, but I have this term to account for inertia. And remember that now this equation, which is the Navier equation for considering inertial forces, these are 3 equations, okay? Remember that we have displacement in 3 directions, so those are 3 equations. But now we are using this vectorial notation, so we just write one line, but those are 3 equations. Okay, so let's try now to solve the wave equations out of this equation. You see, it's not going to take too long. But in order to solve that, we need to do some assumptions. The first assumption I'm going to do is considering a space 1, 2, 3. I'm going to say that we're going to solve this equation only for displacement in direction 1, which are not 0, and all the other displacements are equal to 0. If I want to show more or less what this wave is going to look like, it's going to be something like this. Let me here making schematic of a bar in 3 dimensions. Although I'm showing a bar here, you should imagine this as an infinite medium in all directions. Okay? Here we're just showing one piece of that infinite medium in all directions, but just to make it easier to see. In this part, we're going to have a wave that only consists of displacements in direction 1. Okay? So imagine that we have an element over here. If I have displacement in direction 1 only, what kind of strains do you think we're going to have? But it's the strains in which direction? Which epsilon is going to be different than 0? Epsilon 1 is going to be different than 0. Epsilon 2 is going to be 0. Epsilon 3 is going to be 0. And if we try to see that in this bar, let's assume that there is compression in here. The deformed configuration of this is going to be something like that, only with deformation in direction number 1. At some length from here, because it's a wave, I'm going to have the opposite of a compression, and I'm going to have an expansion, and the deformed configuration is going to look like this. And at an equal distance from the first to the second, I will come back to compression. All right? So I want to plot here now epsilon 1 as a function of x1. What I'm going to see is that at this point, let's say compression is positive, it's that value over here. Let's say expansion is negative, this that value over here, contraction is positive, something like this, right? And if I join the points smoothly, this is going to be an harmonic function, and the distance between these two peaks is going to have some specific meaning, which is called how. I'm pretty sure you guys have heard this word before. So what is that called? That's called the wavelength. And the wavelength goes by Greek letter lambda, and this is called the wavelength. It makes sense, right? Is the distance between the two peaks is the length of the wave, the characteristic length of the wave. Before we move into the equations, what do you think is the shear strain during propagation of this kind of wave? Shear strain is 0, right? So all shear strains for I different than j are equal to 0. And the volumetric strain is not 0. This is very important, particularly for porous media, because as we know, porous media have fluids inside, and whether the fluid can squirt out of the porous medium when the wave passes is very important to characterize the wave propagation in these kind of materials. We're not going to talk about porous media right now, but remember that volumetric strain in that case is very important. It's not the same if the medium is saturated with the fluid or if it is not. So with all these assumptions, now we can write again the Navier's equation, and we are going to write just the first equation, okay? So this is going to be m minus g, and if this is the first equation, the first derivative, the first gradient, just going to be dx1, right? The divergence of the displacement is going to be this one, and then I have plus g, the Laplacian of the displacement. I tend to forget always the second two over here, so let me know if I forget one. And that's going to be equal to density second derivative of u1 2 times respect to time 2 times. Oh, you cannot see that. Sorry about that. So that's exactly that equation. Let me zoom out a little bit. I think that's the maximum I can do. Probably I can move this in. So we just expanded this one for the first coordinate, and this one is going to be the same for all of them. And now it's very important here that now we have u1. According to our assumptions, we're saying there are no displacement in direction 2. There is no displacement in direction 3. So all of these are going to go to 0. And notice that this is going to be second derivative of u1 respect to x1, and this is second derivative of u1 respect to x1. So it's going to be the same. Negative g, positive g, cancel out, and everything we are left with is with m times that. Okay? I'm going to go one step further, and I'm going to write this one on the left-hand side. And on the other side, I have m. I'm going to divide by density, and everything that was left from here was this term, m times that. So this is du1 dx1 squared. And that's the wave equation for this type of wave that by now we can put a name on it. This is a P wave in direction 1. And it's a compression wave, and P comes from primary. Usually P wave is going to be faster than the other wave that we're going to look at, which is the shear wave, which is a secondary wave. Let me show you an animation of this P wave that is going to be very useful to have a feeling about this P wave. Let's see. Where is that P wave? Here. Okay. So let me zoom in here. That's a P wave. That's what we have. I did a schematic for. Now we see that in space, right? Here's the wave. This compression. After some time, expansion and compression again, right? You're looking at this as a function of time. It's very important that now that we look at this wave and the equation that we have, that we see that this is a function of both space and time. So for example, at time equal to 0, there is no strain, but after some time, we do have strain. And if I were to pause this at a given time, there are places in which I have compression. There are some other places in which I'm going to have expansion. Okay? And one more thing the particle motion, notice that it's in this direction and it's in the same direction of the wave propagation. So the direction of propagation is in this direction, direction x, and particle motion, it's in the same direction. So this is the P wave. Let me get out of here, and let's come back to the equation. In this case, I'm taking like kind of a picture at a given time, but remember this is going to change with time. All right? Okay. Let's talk about the solution of this equation. You have a question? No. Let's talk about the solution of this equation. You guys know what is the solution of this kind of equation? Someone good in math, tell me what kind of differential equation this is. I always forget. It's parabolic. I know, but it's parabolic, elliptic, hyperbolic. Whoa, the guy's taking a comprehensive exam. No, they don't remember. Okay, it doesn't matter. Okay, you can find the solution for this equation, and the solution is going to be, as we say, a function of space and time. In this case of x1 and time. And it's going to be an harmonic function where if this is an exponent, this is the same as saying that this is a summation of sines and cosines. So notice that here we have space x1 and time. So displacement is a function of space and time. This is a constant, and what is this? This is a irrational number, square root of -1, right? So this is an imaginary number. You can find the solution through this set of equations, but the short answer is that this is a harmonic function. You know, similar as what we did here, and that this is a harmonic function. We could assume, for example, for a particular case, that u1, let's say, as a function of x1 and t, is just equal to the sine of wt plus k x1. Oh, I didn't talk about these two parameters. Notice that those are just parameters of proportionality, one for time and one for length. Okay? But those are just constants. The variables are t and x1. We'll talk about the physical meaning of those in a sec. But one is a proportionality parameter with respect to time, for which you have an entire cycle. The other one is a proportionality parameter with respect to space. Okay. So, my objective is going to be to compute these two second derivatives. Okay, let me try to do it here so we don't have to do it in another piece of paper. What is going to be the second derivative of u1 respect to time 2 times? I know you can tell me what this is. Negative omega squared sine of that function, right? And what about the second derivative of u1 respect to x1 2 times? Sine wt plus k x1, right? Well, let's now just replace those two equations into our main equation above. And let me write here, so du1 dt 2 times divided the second derivative u1 respect to x1 2 times. That's just going to be equal to this parameter divided this other parameter, all of that squared, right? And actually this is going to be equal to m over density, right? And let's go a little bit further here and talk about the physical meaning of these two. Omega is what is called an angular velocity, or an angular, actually it's an angular frequency. Yeah, and this is equal to 2 pi divided the period of the wave in time. I'm going to do a schematic about this in a sec, okay? But remember that we have a wavelength and we have a period. And kappa is what is called the wave number, and kappa is equal to also 2 pi. Remember, the 2 pi comes from here to making a full cycle, so you get to the other peak or trough, divided the wavelength, right? So let's now use these two into there, and we will see that frequency divided by that wave number is going to be equal to 2 pi, goes away, and then this lambda is going to go to the top. It's going to be lambda divided by t, right? Let me add here the square, and here the square equal to m over density. And now what do we have? We have a distance divided by the time. And as I was telling you before, if we were to look at epsilon 1 with time, we will see that this one goes to peaks and troughs, and the distance between these peaks is the period. So what do you think is going to be a wavelength divided by a period? Is the speed of the wave, is a velocity, and from here we get that the velocity of the p wave is going to be equal to the square root of m divided by density. So I came up with this solution yesterday, but with the help of my PhD advisor. I have to tell you the truth. But this equation shows you that in order to have equilibrium between inertial forces and elastic forces, the velocity of that wave has to be proportional to the square root of the stiffness modulus. So this is basically what I wanted to get to. We know what is a wave. We know what is a period of the wave. We know what is the wavelength of the wave, and we know what is the velocity of the wave too. Let's see, how are we doing with time?
Quarter till.
Okay, so I think I do have time. So let's try. That was for the P wave, okay? Let's go now with the shear wave. For the shear wave, it's going to be very similar. And please remind me to talk about frequency later on. Okay? But instead of having displacements in direction 1, now we're going to have displacements in direction number 2, but propagation of the wave in direction number 1. Okay? So let me remind you that here we had assumed these directions 1, 2, and 3. If I have an element of the solid, and let's make that at a given snapshot, at some point I'm going to have displacement. Well, in this case we're going to have displacement direction number 3, like this. This is the deformed configuration. After one wavelength I find the same, and at half a wavelength I find the opposite. Again, this one has a given wavelength, and in this case now displacement in direction 1 is equal to 0, displacement in direction 2 is equal to 0, and displacement in direction 3 is different than 0. Notice that now we have wave propagation in this direction, but there is displacement in that direction. What is going to be the volumetric strain in this case? It's going to be 0, right? Because those are just shear strains. Let's try again the Navier equation for equilibrium, but we're going to write the third equation for x3, du1, dx1, du2, dx2, du3, dx3. What do you think is going to be the value of these three? They are all going to be 0, right? So I'm going to cross them over in just a sec. du3, dx2. I think I did a mistake in the previous equation. Let me come back there. I just noticed it from this one. Let's see. This one is u1. And why they are 0? Because there is no variation in direction 2 of u1. u1 stays the same. There is no variation in x2. There is no variation in x3. That's why those are equal to 0. Okay, so let me come back over here. We just said these are 0 because all of these, remember, these are all volumetric strains, and all of those are equal to 0. And in this case, we just have shear strain in the plane 1, 3. So this is 0, this one is 0, and we just get now that the variation of u3 2 times respect to time is g divided mass density, and times du3 2 times respect to x1. You see, I always forget the 2's. x1 over here. And same as before, this is going to tell us what the shear wave is, and this is going to give us the shear wave velocity, which is the ratio, square root of the ratio of the shear modulus divided by mass density.
Should that be delta t squared in the second derivative for the equation in the box?
Yes, thank you. And now we also have the shear wave velocity, right? So there are many applications of elastic wave velocity in geophysics, in civil engineering, in petroleum engineering, generally in physics, in geology. For us, what I like that we do is that we learn how to compare what are called the static moduli that we'll get from applications that involve quasi-static and large strain loading to measurements that we can do with dynamic measurements or with waves. And that's the objective of project number 9, okay? So for project number 9, I don't want you to stress out about that one and solve it before the exam. You can solve it. I put a deadline on Friday in the evening or really at night, okay? And basically what you have to do is you have to use wave velocity measurements in order to come up with something which is called a dynamic to static conversion. Basically what we want to do is we want to use BP and BS from Seismic, from cross-well measurements. You can do this one also from passive measurements. So when I mean seismic, I mean active. Or from well logging. With all these type of geophysical surveys, you could measure BP and BS in the subsurface. And from there, we want to get what is going to be the Young modulus that we're going to call. So of course, if it is BP and BS, this is something that we call dynamic. We want to get the Young modulus and the Poisson ratio that will resemble the static conditions. Let me tell you that this is a very complex problem, okay? But at some point, if you want to do some practical applications, you have to simplify it. And what is usually done, at least in petroleum engineering, that works more or less well, it's not perfect, okay, but works more or less well, is to use data from well logging and data. Here you'll get this one from the laboratory. In order to get sometimes a constant, sometimes a function, a coefficient that links those two, where that coefficient is going to be always, if we write an equation, for example, very simple equation, E static equal to FDS dynamic, this coefficient is going to be less than 1. So why is it less than 1? Again, there are many reasons for that. There is dispersion. I'm going to talk a little bit about this after I finish with this. Basically, variation of wave velocity with wave frequency. There is strain magnitude, and closely related to that, also you can have plastic strains, and related but not only to dispersion is viscoelasticity. All of those are going to make this factor less than 1. So basically what you have to do in project number 9 is to use a laboratory test in order to come up with this relationship. I have given you data for a triaxial test done in the laboratory downstairs, in which I'm giving you stress, deviatoric stress, as a function of strains. It's a typical triaxial test in which you load it and then it starts to deviate and reaches a peak. And if you were to monitor the radial strain, you will see something similar to this. But it will do something like that. Okay, that went too much up. from that laboratory data, you can get the Young modulus and the Poisson ratio, right? You know how to do that. And what I'm asking you is that before the point of 50% of strain of the peak stress, take a couple of values here. Let's say 5. Measure the Young modulus at those locations. This is a real rock, so it's not going to be exactly linear, okay? These values are going to be similar, but are not going to be linear. From here, you get static Young modulus. And if you use the radial strain, from here also you're going to get the static Poisson ratio. You know how to do that, right? Relatively easy. Let me tell you why 50%. 50% because in many of these rocks what we see is that although at the beginning when you start to load them they start to shrink, at some point they go into dilation. And that's more or less at 50%, 60% of the peak stress. And that tells us that the rock is already failing. Although it hasn't reached the peak, there is something going on inside that is causing the rock to fail in shear.
So
Robert.
would you say that something like 50% of the ultimate yield, the ultimate strength
Yes.
is the yield strength essentially?
Yes.
Of the rock?
Yes. So that in order to measure this elastic moduli, we should remain in the elastic range. And the elastic range is more or less in a domain of less than 50% of the peak stress. All right. So you know how to do this, right? We have seen this so far. The new thing is where it comes now. Together with this data, as a function of time, I'm giving you at a given time and give you measurements of P wave and S wave. So you're going to see that every 30 seconds you're going to have data of something that looks more or less like this. Where this is going to be probably I exaggerated this. Don't consider that, okay? This is going to be what we call delta T for the P wave, and at that same time you're also going to find a file that looks more or less like this, in which you can measure the time for the S wave to arrive. If you know the length of your sample and you know the time it takes to the wave to get to one side to the other, then you can calculate the velocity, right? But there is one more thing to do over here. In this experiment, we send the wave from crystals that are a little bit further away from the rock. So there is going to be a delta P correction and a delta S correction that you have to use in order to correct this delta T and delta S, okay? If I remember correctly, I don't think I do, but it's more or less 4 microseconds and 6 microseconds. So for example, if you go to the actual data and it tells you that this one is 20 microseconds, well, the actual time for the wave to go from here to there is 20 minus 4 is actually 16 microseconds, okay? And the P wave, the actual P wave, is going to be, for example, from here, BP, the delta TP, wait. It's going to be the length of the sample divided delta T P minus delta TP correction. And the same for S. Okay? So we have the static moduli, we have the P wave and the S wave. What do you do next? We're going to use the theory of linear elasticity. All the time here we're assuming linear elasticity. And for linear elasticity, how many parameters do we need to define a solid? Just two, right? For example, Young modulus and Poisson ratio. But notice that we could also use BP and BS. Those are two independent measurements, and with those and density, we can calculate what is the Young modulus and the Poisson ratio. So if you're using waves, you will see that the dynamic Young modulus is going to be equal to this equation, where everything I do to go from here to there is just writing M as a function of E and the Poisson ratios, right? You know how to do that. And G also as a function of E. I don't remember. I think it's something like this, right? We're gonna check it in a bit. Yeah, I think that's about it. That's all I do in order to get from here to there, and these are the equations that we get. And with these equations now you can calculate those two properties, Young modulus and Poisson ratio, from BP and BS, and utilizing the density. And finally, after you do all of this, I'm asking you to do it for just 5 points, okay? I'll give you many more ways than that, but just do it for 5 points. Select some 5 points over here, do it for 5 points. The final thing is to compare what is the static to the dynamic. And although there is some logic in comparing the Young modulus to Young modulus, there is an open discussion about what's the meaning of comparing these two Poisson ratio. Actually, Poisson ratio measurements in triaxial tests are kind of sketchy, iffy. I don't know how you may call it. With waves, it's fantastic, okay? But for larger strains, it's very complicated, okay? It's not easy. But the concept here is that if we have a material with no dispersion, with no plastic strains, with no viscoelasticity, with nothing of that, you will expect to see a correlation 1-to-1, right? But for real materials, what you see is actually, as I was telling you before, that for a given type of rock, you will find that the static is lower than the dynamic, and the relation between those two is going to give you, if this is 1, your proportionality factor FDS. And this one, I'm not going to write everything in there, but you can do that, okay? So you can get the same relationship. Whether it makes sense or not, that's something that it's open and depends on the laboratory conditions.
Is FDS supposed to be the same for both, or would you have different conversion factors?
No, those are going to be usually
They're gonna be
different.
different.
Yes, yes.
That's what I figured. I just wanted to make sure.
Most times, what is done is you will assume that the static is the same as the dynamic, and just use the dynamic. Okay, so probably I forgot to say why we're doing this, right? we are trying to use dynamic measurements to represent static measurements because we have much more availability to dynamic measurements. We can measure dynamic measurement as a function of space. Imagine if you have a wellbore, you can get continuous measurements of BP and BS. So if there is, for example, here some characteristic layer that is changing that BP and BS, we can have a continuous map of that. With some other more advanced techniques, for example, if you have a cross wellbore, one wellbore here, one wellbore over here, you can even resolve not only the variation in this coordinate, but also in that coordinate. You can do a tomography, so you can get the 2D idea. And if you have 3 wells or more and you have some other data, you also can get it in 3D. So we have much more availability to dynamic measurements than to static measurements. And in order to build a continuous model, what we do is to utilize these dynamic measurements somehow fitted to represent what we actually want to model in order to have a continuous model of the subsurface. So I think that with that, one more thing. I said about dispersion, right? A very important concept here, and since we're not talking about this is well logging, right? And this is crosswell, and you could also do seismic to get these properties, is to talk about frequency of the waves. What is the typical frequency of seismic waves?
Are we talking about like earthquakes or sledgehammer?
6. I'm talking for seismic prospection.
Well, like if you're doing MISW with a sledgehammer, probably from about 10 hertz to 100 hertz.
Okay, I like the number. So this is measured in hertz, where a hertz is 1/2, right? Say again, what number did you say?
They said like doing MISW with a sledgehammer, like about 10 hertz to 100 hertz.
Okay, so from here to there, and what about natural earthquakes?
Dominant part is lower.
Yeah, I mean like for micro-seismicity and stuff, you can get down to like 0.1 hertz.
Okay. Well, probably
Or even
you're forcing me to
measure.
extend this. So let's say earthquakes somewhere over there.
Yeah.
What is the frequency for well logging? The guys working in well logging. No one working in well logging? No? It's about 100 hertz. And it can get a little bit higher sometimes. What is the frequency for laboratory measurements?
For resonant columns, for sand is less than 200 hertz.
Well, resonant column is a very special device, okay? And it's actually it's a very, very, very smart device. And what is the highest for a resonant column?
I think for rock we can go like 300 hertz, 400 hertz.
Okay, so let's put resonant column over here.
The lowest one we can go to like 30 hertz, 40 hertz.
So resonant column is a device in which you have a sample and you do torsion, and you measure the shear wave, the torsional shear wave, which gives you the shear wave, and was invented by a professor here in UT called Ken Stockey. It's a very smart device. What about ultrasonic velocity in the laboratory? Anyone knows? it's more or less in the order of the kilohertz to the megahertz. And this is actually the data I'm giving you. It's laboratory ultrasonic data, which you, as you notice over here, it's orders of magnitude higher in frequency than some of the applications in which we are interested. For example, if we're interested in depletion, what is the frequency of a depletion process? Like somewhere over here, right? It's a period would be in the orders of 10 years. So very, very small. If we are talking about some hydraulic fracture applications, for example, that take place in deformation in terms of hours, also frequency is very low. But even when we try to compare well logging to lab ultrasonic, these frequencies are quite different. And in order to establish a relationship with those, and ignoring for now plastic strains, what is usually seen is that the higher the frequency, the higher the velocity is. And this is a phenomenon where the velocity depends on the frequency, which is called dispersion. And knowing that dispersion curve can help you establish a relationship between these two. Okay, all right, guys. I think this is the end, and we're gonna have the exam on Thursday, right? And I don't want to stress you out also about the presentations. So I'm gonna send you instructions about that after we have the exam. I'll try to do that today, okay? But don't worry, don't work on that right now. Just work and study for the exam. Okay? All right.